Hi, I'm Nenad Petrovic, a teaching assistant at Faculty of Electronic Engineering, University of Niš in Serbia, Department of Computer Science. Now I will present you the paper that we wrote together with my colleagues from Telecommunications Department, Samir Konicanin, Dejan Milic and Suad Suljovic, and Stefan Panić from University of Priština, Faculty of Natural Sciences in Kosovska Mitrovica. The topic of this paper is GPU-enabled framework for modeling, simulation and planning of mobile networks in smart cities. We all know that mobile networks have significant impact on almost any aspect of our everyday lives, from healthcare to transportation and business. On the other side, the number of mobile service users and requirements increase continuously, which poses many challenges and gives a strong pressure to service providers and operators. However, establishing fast, stable and secure connection in large-scale mobile network deployments is quite challenging, as we have noise, interference and fading that dramatically affect the quality of service. We have mobile base stations that are actually responsible for these deployments. Each of them has some distinct parameters that need to be set in order to maximize the overall quality of service. However, setting these parameters manually is unfeasible in most situations, especially when it comes to commercial deployments with thousands of base stations. Therefore, adoption of some approach that will automatize the procedure of tuning these parameters is really required. On the other side, testing and evaluating the performance of these deployments is quite costly and time-consuming. Therefore, simulation approach can be highly beneficial. In this paper, we present a framework that covers the aspects of modeling, simulation, and planning of mobile networks within smart city environments, aiming time-critical use cases and scenarios like autonomous vehicles, video surveillance by drones, and similar. The main advantages of the proposed approach are, in the first place, intuitive graphic modeling notation for mobile service infrastructure operators, and that gives a possibility to easily manage and define quality of service adaptation strategies. On the other side, it's run in a web browser without any additional tools required and knowledge of programming languages, so the learning curve is not as steep as in most cases when it comes to other simulation solutions. And finally, as we aim time-critical scenarios, we want to make use of faster GPU-based calculations. Related work. The work presented in this paper relies on my past work that is actually a proactive approach that combines the synergy of deep learning-based predictions and linear optimization. So the first work that presented this approach was optimal blockchain-based energy trading within smart grids. I used deep learning-based predictions of energy consumption within the household and linear optimization for energy trading between the households. And on the other side, resource planning during COVID-19 pandemic crisis, we had the prediction of number of new COVID-19 cases within city or even deaths of citizens within the city. And on the other side, linear optimization was used for minimal cost exchange of resources such as masks or test kits between the cities. However, the adoption of this approach is completely novel in domain of mobile network simulation and planning as far as we know. Background. There are four key concepts that are behind the proposed framework. First, we have deep learning. It covers a family of various machine learning techniques and algorithms that are based on artificial neural networks. For implementation, we rely on GPU-enabled TensorFlow for Python to make use of our GPU as much as possible and have faster calculations. It's used for consumer demand prediction, actually how much is the service demand in a number of users within the particular smart city area. We have linear optimizations that aims to achieve the best possible outcome with respect to some requirements that are represented by linear relationships. Ample modeling language is used to define optimization models and like solver based on simplex method to solve them. It's adopted to enable optimal base station allocation at smart city locations. GPGPU, actually general purpose graphical processing unit programming, makes use of hardware for graphics for some other tasks apart from graphic rendering. For implementation, we rely on NVIDIA CUDA and C programming language. And apart from deep learning that is powered by GPU, we also leverage it for fading calculation to indirectly calculate quality of service this way. And software-defined radio is the final concept. It's actually radio that has the ability to be reprogrammed on the fly, as most of its capabilities are implemented within the software for some functionality that was never anticipated before. So our idea is to use SDR-based architecture to accept the commands that our framework generates and therefore enable dynamic adaptation of quality of service to satisfy consumer demands. Framework overview. The first step is modeling of a smart city resources with respect to base station parameters and their allocation, and on the other side, the consumer demand. So the other step is demand prediction. We use historical past data within a given location to predict service consumption in future. Fading calculation enriches the linear optimization model with quality of service values. So we use environment factors like that, also like obstacles and distance to base station, to actually finally calculate the quality of service apart from taking fading into account. When we get both the demand prediction and quality of service values, we perform linear optimization to allocate the best possible types of base stations for given city locations. Then afterwards, when linear optimization is done, the results are taken as input of SDR command generator in order to generate the commands that will be applied to SDR infrastructure. Now, let's take a look at the modeling environment. First, I will show you the domain-specific modeling notation that we introduced. So, the main concept is a city map, and it has many locations within the city. Each of these locations has objects. The objects could be obstacles that affect quality of service, like buildings. Also, we have base stations that are actually responsible for network deployment. They can be either macro diversity or micro diversity to tackle different types of fading, like fast fading and shadowing. They have different parameters like energy consumption, power, capacity, and quality of service threshold. And finally, we have network service consumers that are connected to these base stations, like autonomous cars, pedestrians, drones, or surveillance cameras. On the other side, we have environment factors that are quality of service drop functions that actually define how quality of service drops as some environment factor varies. Like distance factor defines how quality of service changes as consumers move from a base station. Actually, how the distance increases, then the quality of service will be dropped. Moreover, we have demand factor that actually defines how quality of service drops as number of active user for a base station at a location increases. On the other side, we also have fading that is taken into account. Two types of fading are modeled: fast fading and shadowing. And for each of fading types, moreover, that are like Nakagami, M, and gamma fading, or kappa mu, we also have ability to calculate different types of statistical measures describing the effect. These statistic measures are used later for quality of service, for overall quality of service estimation. And finally, one more aspect is considered that aims also infrastructure operators, that is actually quality of service adaptation strategy. It has an event that is some change in the environment that triggers the strategy. And on the other side, we have the response that is actually a parameter tuning approach or execution of a particular optimization procedure. So this event is modeled by a threshold value that is actually a threshold for quality of service. And if the value drops below, then a corresponding strategy will be taken. Now let's see how the modeling and simulation tool actually looks like. Here you can see a user interface, an example of a city map. We have on the left side the city map with several locations like Science, Technology Park, Airport, and Downtown. On the right, we have the details for each of these locations. As you can see, I enlarged the downtown after double-clicking on the icon for downtown, and you can see the service consumers, like two cars and surveillance camera, for example, the buildings that are obstacles, and a base station that is actually selection combining base station macro diversity type. And here is the demand in number of users and the quality of service threshold and price for this base station, for example. Also, other parameters can be valorized, like energy consumption and so on. When it comes to simulation mechanisms, quality of service, new value of quality of service is calculated taking into account the product of previous quality of service and product of factors that affect quality of service, like fading, distance, and number of users, and their impact coefficient. For each of them, we assign an impact coefficient that says how much actually this factor affects the overall quality of service. In case that new quality of service drops below the given threshold defined by the operators, then corresponding adaptation strategy will be taken. Now let's see the demand prediction module. So the data set is shown on this slide as a header of a table. Independent variables are location ID, base station type, like is it macro or micro diversity cell, or which kind of technique it's leveraged, like decode and forward, selection combining, and so on. The number of days within the year when the consideration was made, hour actually within the day when the service demand was observed, and the predicted values on the other side are the number of connected users and average quality of service for a given location at a particular day and hour. And the training set was 70% of the available data, and test was 30%. Now let's see what is the structure of GPU-enabled fading calculation module. So quality of service is calculated by leveraging fading indirectly. So we multiplied the quality of service, the previous value, by a fading impact function that returns a value between 0 and 1 based on some value of statistical measure that describes fading effect, like outage probability. For implementation of these mechanisms, we implement GPU kernels that in CUDA and C programming language, and here you can see on this slide a placeholder for a kernel. So the fading function in listing actually represents the specific statistical measure that describes the fading effect. So for each type of fading and statistical measure, we will need to use different type of kernel that actually implements the corresponding formula. Now let's see the optimization model. So when it comes to decision variables, we have decision variable x that has value 1 if base station BSI will be placed at location LJ. Otherwise, it's 0. The objective function aims to minimize the overall sum of costs that consists of energy consumption of base station, actually the distribution cost to a particular location, and quality drop that is actually a ratio between the maximal quality of service for a particular area and the current quality of service. There are three constraints. The first constraint says that each location we must have exactly one base station. The second constraint says that each of the available base stations can be located at most at one location. And finally, the last constraint says that we have actually to satisfy the consumer demand at each location by providing a base station that is able to do that. But the value D, that is the demand, it's a predicted demand that is output of deep learning based prediction module. And now on the right, you can see the ample code that actually implements the described model. Now let's see evaluation and results. A laptop with given characteristics was used for evaluation purposes. Two aspects of evaluation were considered: execution time and cost reduction on one side, and on the other side, the quality of service improvement after the optimization was performed. Different model sizes were considered, as you can see in the first column of left table, different fading times, kappa, mu, Nakagami, M, and gamma. And for these different models and model sizes and fadings, we measure the time. So the prediction time is actually the time needed to predict the service demand for given locations in particular model, and optimization time is actually the time needed to perform optimization once all the values are actually available. And acceleration is actually the acceleration achieved using GPU approach for fading calculation. So as you can see, it's quite significant, like averagely 30 times. Even in two cases, it performs better than one of the related works that were mentioned in the paper. When it comes to cost reduction, you can see it varies from case to case, from model to model. It actually depends on the concrete instance of the problem. Actually, when we observe the two models used for same type of fading, we can see that acceleration was increased for a larger data set, as GPU is much more efficient and its impact is much more significant when it works with large amount of data. And finally, on the right side, we can see the quality of service improvement for a different number of consumers within the environment. We used different types of base stations using different techniques. They call them forward and selection combining. The given threshold for quality of service was the limit when optimization strategy was triggered. And finally, in the fourth column of the second table, we have quality of service improvement percentage. That is the actual ratio between the current quality of service and the improvement once the optimization and other tunings were performed. Conclusion and future work. According to the initial results, the proposed framework seems quite promising, as it provides means to calculate the quality of service parameters even timely and react accordingly to improve consumers' experience and quality of service by executing different parameter tuning or optimization strategies that are applied to software-defined radio architecture. A domain-specific graphical notation is introduced in order to make modeling, simulation, and resource planning more convenient to the operators. Moreover, they are able to have elements of policy-based management that is quite intuitive by using graphical notation and define strategies that will be executed in particular scenarios. However, when it comes to comparison to other frameworks and solutions, one of the main advantages is that the proposed framework is quite general and offers much more capabilities for extension than the ones that are actually available. When it comes to resource allocation and optimization, our approach is quite simple and simpler than some other approaches, but unlike other approaches, it provides results timely, as very complex procedures and large models are actually bottleneck to do that. And moreover, we also leverage GPU which is not the case in all of the available simulation and planning tools. However, as I already mentioned, we haven't used hardware as the real architecture to test the solution, and we want to plan and do that in future. However, we used mock commands within the simulation environments to simulate the quality, to the adoption of software-defined radio, but in future we would like to use concrete SDR-based architecture. Now let's proceed to questions and answers. The first question is, can you comment on the quality of experience requirements in smart cities related to innovative mobile services? So I already mentioned many times that in this paper, the topic of interest are time-critical scenarios like autonomous cars that send enormous amount of data for processing, like computer vision algorithms need to have a video stream timely in order to avoid obstacles and avoid some tragic consequences in that case. Moreover, drones that are used for observing city locations are also quite interesting scenario, or even mobile base stations based on drones could be some potential future research and use case that is used in some areas that are not easily accessible, even not within the city, maybe in some distant areas, but we can also make use of that and leverage the proposed framework in similar way. And finally, video surveillance cameras within the city are something that where time reaction is quite critical. So in order to detect some events within the environment, we need to actually provide the data as quickly as possible for the analysis. And what would be the delta of the framework implementation in order to support the other types of accelerators like DSPs or tensor processing units? When it comes to tensor processing units, the additional work needed would not be so difficult and time consuming, as we already rely on TensorFlow, and as far as I know, tensor processing units are actually leveraging TensorFlow. So I think it would not require too much time to fix and make possible the usage of deep learning module on tensor processing units. However, for other purposes, it might require more time, but for deep learning, it wouldn't be a problem. But when it comes to other types of accelerators like DSPs or FPGAs or some other supercomputers or high performance computers, the additional effort might be not so small. So it depends on the computing paradigm that is used behind the hardware. But for example, if we have some specific FPGA, we would need to rewrite the kernels to comply with the given paradigm of programming and structure of hardware, and also the software environment that is used. So we cannot use the same CUDA kernel for that purpose. Thank you for your attention. This work has been supported by the Ministry of Education, Science and Technological Development of the Republic of Serbia.